Welcome to the course on an introduction to information theory. I am Adrish Banerjee from Indian Institute of Technology, Kanpur, and I am going to teach this course. Now in today's lecture, I am going to give you a brief overview of the contents of this course, what does information theory deals with, and I am also going to talk about some of the books that we are going to follow in this course. So, the first lecture notes that we are going to follow in this course is by late Professor James L. Massey. These are Applied Digital Information Theory 1, and these lecture notes are available at this website, which is maintained by ETH Zurich. These are very nice sets of lecture notes on information theory and very easy to read and understand. Another classic book on information theory is by late Professor Thomas Cover and his student Joy Thomas. It's called Elements of Information Theory, second edition, and this book is available in cheap Indian edition. It's a very classic book on information theory, and it covers most of the topics that we are going to cover in this particular course. Some of the other books, very nice books. This book by Professor Robert G. Gallagher, it's a very classic book on information theory. You can also follow this book, or there's a modern book on information theory which contains some modern topics which obviously we would not be covering in this particular course, but a very nice book on information theory by Professor Raymond Young. You can also use this book. Another nice book on information theory is the book by late Professor David McKay. Again, this book is very easy to read and very nice book. An old classic on information theory is the book by Professor Robert Ashe. This does not cover all the topics that we will be covering in this course, but whatever topics it covers, it presents it in very nice fashion. Another classic book on information theory is by Professor Chizar and Kroner, called Information Theory, published by Cambridge University Press. I strongly suggest you read this Collected Papers of Shannon. It's a very nice collection of papers by Claude Elwood Shannon, the father of information theory. This is edited by Sloan and Weiner. A very nice collection of papers by Claude Shannon. Now there's a separate book on network information theory by Professor Abbas Al-Gamal and Yong Han Kim. They also have a set of lecture notes which are readily available on the internet on network information theory. That's a very nice reference on network information theory. And finally, this book covers both classical as well as quantum information theory. Though we will be covering in this course only classical information theory, but those of you who are interested to learn quantum information theory can refer to this book by Emmanuel Desourve. Okay, so let's now talk about what are the course content for this particular course. So we'll first start off with quantifying information. What is information and how do we quantify information? So we'll talk about Hartley's measure of information and Shannon's measure of information, and then we will talk about entropy, relative entropy, mutual information and their properties. After that, we'll talk about some information inequalities, Jensen's inequalities, log sum inequality, and some other results such as Fano's lemma, which we will be using subsequently later on to prove some other results. Then we will move into the problem of source compression, source coding. So source coding can be from block to variable length coding, variable to block length coding, block to block length coding, and variable to block variable length coding. So that depends on whether the input sequences of fixed length which we are calling a block, or where input length is variable. That is this block, and this block to variable whether the output is of variable length or fixed length. So we can get compression if we take a block of data. We can get compression by representing blocks which are happening more frequently by lesser number of bits, and blocks which are happening less frequently by larger number of bits. So in that way we can reduce the number of bits required to represent a source. So we will talk about optimal block to variable length coding, which is your Huffman coding. We will prove the conditions for optimality, what is the minimum number of bits required to represent a code. We will also talk about variable to block length coding, and for a specific instance where the message can be parsed in a particular fashion, we will talk about an optimal variable to block length coding in that particular instance, which is what is known as tungsten coding. We will also talk about variable to variable length coding, which are very prominently used in lot of source compression algorithms. So in particular we will talk about arithmetic coding and Limpel-Zerf algorithms, which comes under the class of universal source compression algorithm. You do not require any knowledge about the prior source distribution of the source that you are trying to compress. We will also talk about block to block length coding. Now if we are doing block to block length coding, to get compression obviously we are encountering a lossy compression. Now we will show that there are some sequences which are more likely to happen. Given a source distribution, there are some sequences which are more likely to happen from that particular source, and some sequences are less likely to happen. So when we do block to block length coding, we will try to encode, assign individual code words to all those sequences which are more likely to happen, which we call as typical sequences, and of course for all other non-typical sequences we will just assign one particular code word. So when we transmit a typical sequence, the decoder will be able to decode that sequence, whereas for a non-typical sequence we would not be able to distinguish what sequence was transmitted, and hence this is an example of a lossy source compression. We will also talk about what is collectively known as asymptotic equipartition property. This is a information theory analog of law of large numbers. We will talk about what are these properties and what is the consequence of these properties. Then we will move to source compression for sources which have memory. So we will exploit basically correlation between temporal correlation between the bits that are coming out of source. We are going to exploit that correlation to design our source encoder. So this will be our coding for sources with memory, and we will take a very simple example to illustrate that. After this few lectures on source compression, we will now move to channel capacity computation. So channel is the medium over which we are communicating. So how many bits we can transmit over a communication link, that's basically your channel capacity. So we will talk about some very simple channel models, and we will talk about how to compute the channel capacity. Then we will move from discrete random variable to continuous random variable, and we will define entropy for continuous random variable. That's basically what is known as differential entropy, and we will consider an example of a very commonly used channel, which is additive white Gaussian noise channel. We will compute the capacity of additive white Gaussian noise channel. Next topic deals with what is known as rate distortion theory. Now if you have a real number and you try to represent that real number, if you want to represent it, you require infinite number of bits, right? But if you try to represent that real number with finite number of bits, then essentially you are introducing some sort of distortion. So how do you find out that your representation using fixed number of bits is a good representation of your real number. So you need to describe a goodness measure between your original real number and its representation. That's basically known as distortion measure. Now rate distortion theory deals with, if you have a source and a given distortion measure, you are interested in knowing, for example, what is the minimum average distortion that can be achieved for a given rate. So given a distortion measure, we are interested in basically finding out, or we can alternatively say that given a average distortion measure, you want to find out what's the minimum rate that you can achieve. And finally, if time permits, we are going to talk about network information theory. Now earlier here when I talked about channel capacity, I am going to talk about point-to-point channels. So there is one transmitter and one receiver. So we are going to characterize the capacity of such channels. Now think of scenarios when you have multiple senders and multiple receivers. How do you find out capacity of such channels? Or let's say you have multiple senders, multiple receivers, and you want to do distributed source compression. So all these problems comes under this network information theory. So this is roughly the syllabus that we plan to cover in this 20-hour lectures, span over 8 weeks. So what can you expect after going through this course? You should be able to understand or find out what are the fundamental limits of communication, at what rate we can reliably communicate over a communication channel. You should also be able to find out what are the fundamental limits of data compression. So, for example, if you want to do lossless compression, what is the minimum number of bits required to represent a source? Or you want to do a lossy compression, given an average distortion measure, basically what is the minimum number of bits you require to represent a particular source. In the process, you will also come across some practical algorithms for source compression, and you will also learn few mathematical techniques, how to prove theorems and things like that. So let us look at a block diagram of a communication system and see where does information theory, what are the problems that information theory deals with. So what are the various steps involved in communication? So we can roughly say that communication involves 3 processes. The first is encoding a message. So given a source, you want to efficiently represent that source using a fixed number of bits. That's encoding. And then once the message is encoded, you want to transmit it over a communication link. That's basically this point, transmitting the message over a communication link. And finally, the bit that has been transmitted over a communication channel, that will get corrupted due to noise. So at the receiver, you would like to decode and estimate what was the message that was transmitted. So roughly in any communication, these are the 3 basic steps involved. So information theory answers 2 fundamental questions in communication. Number 1, what is the ultimate data compression that you can achieve? So what is the minimum number of bits given a source? What is the minimum number of bits required to represent the source? And the other question that it answers is, what is the maximum rate at which we can transmit over a communication channel, and still at the receiver we should be able to reliably decode that message. So before we go into the block diagram for digital communication system, let's first intuitively try to understand what is information. So I'm giving you an example. Let's say you have a coin which is a biased coin. So this is a coin which has both the sides head, and I flip this coin and ask you to guess what is the outcome. Does this flipping of coin convey any information to you? The answer is no. Why? Because it is a biased coin, you know both sides are head. So no matter what I flip, I will always get a head. So this does not, my flipping of coin does not convey an information, because you know beforehand that you will get a head, right. If this would have been an unbiased coin which has head on one side and tail on one side, then flipping of coin would have conveyed information, because you do not know whether head is going to come or tail is going to come. Let us look at a source which produces these bits 3, 1, 4, 1, 5, 9, 2, 6. Does this convey information? Again, in this case, these are basically representation of this number pi, 3.1415926. So if I give you these numbers, you know this, I am giving you basically representation of pi. So this again doesn't convey any information to you. So why doesn't it convey any information? Because there is no uncertainty in the source. The outcome of this experiment is known. So Shannon's information theory regards only those symbols as containing information that are not predictable. So as I give an example, if you have an unbiased coin, or let us say you have an unbiased dice, if you roll the dice, rolling of the dice, and I ask you to guess what the number is, that event conveys information, because you do not know when I roll an unbiased dice whether I am going to get 1, 2, 3, 4 or 5 or 6. Now let us take a very simple example to illustrate how we can do encoding of information. So as I have written here, we are going to use the statistical structure of the source to represent the output efficiently. Now what do I mean by statistical structure of the source? So clearly, if we are interested in source compression, we should try to represent sources which are occurring more frequently with lesser number of bits, and outcomes which are happening with less probability. We should use more number of bits to represent that. So let us take an example. I have a bag that contains black balls which are 50%, red balls which are 25%, blue balls which is 12.5%, and green ball which is 12.5%. So half the balls are black balls, 1/4 of them are red balls, 1/8 are blue balls, and 1/8 are green balls. Now from this bag of balls which has black color ball, red color ball, blue color ball and green color ball, I am randomly picking up a ball and showing you the color of the ball. Okay. Now I am asking you to convey that information, convey the color of the ball. I want to encode that information. So I have a bag of balls, I am picking up a ball randomly and showing you the color, and I want to encode the color of the ball. That information I want to encode using bits. So how can I do that? So I said a simple encoding, which I call a dumb way. I will explain why this is a dumb way. A simple encoding would be as follows. Now how many different colors of balls you have? You have black ball, red ball, blue ball and green balls. So you have 4 different types of balls. So very simple encoding could be, I would use 2 bits to represent the color of the ball, because I have 4 possibilities. I can use 2 bits to represent. So for example, I can use 0, 0 to represent black ball, I can use 0, 1 to represent red ball, I can use 1, 0 to represent a blue ball, and I can use 1, 1 to represent a green ball. Now if I do this on an average, I am requiring 2 bits to represent a color. Now why is this a dumb way? Please note that 50% of my balls are black. So when I pick up a ball, every second ball is likely to be a black ball. Now this encoding which I did here does not take into account the frequency of the color which comes out. So clearly you can see, if I pick up a ball, I am more likely to get a black ball than let us say a green ball, right. But I am using 2 bits to represent green ball, I am using 2 bits to represent black ball also. So that is why I said this is a simple encoding, but it is a dumb way of encoding, because I am not exploiting the fact that 50% of my balls are black or of black color. So ideally what should I be doing? I should be representing black color with less number of bits and green color with more number of bits, because black is occurring with more frequently. So a smart way of doing could be, so I am using 0 to represent a black ball, I am using 1 0 to represent a red ball, I am using 1 1 0 to represent a blue ball, and I am using 1 1 1 to represent a green ball. Please note, none of these bits which I am using to represent a number is a prefix of any other code. For example, if I get a 0, that is a black ball. Now note, none of these are starting with 0. Red does not start with 0, blue does not start with 0, green does not start with 0. Similarly, look at the coding for red ball. I am using 1 0. Now note, blue does not start with 1 0, green does not start with 1 0, and I am using 1 1 0. Clearly green does not have 1 1 0 as a prefix. So there will be no confusion in decoding this particular stream encoding scheme. Now on an average here I require 1.75 bits per color. How did I compute that? Now for black I require only 1 bit, and black is happening with probability half. For red I require 2 bits, and red is occurring with probability 1 by 4. Blue I am using 3 bits and it occurs with probability 1 by 8. So that is this. And similarly green balls, I am using 3 bits to represent green balls and they occur with probability 1 by 8. So this is my average number of bits required to represent this color, and this comes out to 1.75. And please note, so here I am using 1.7 bits per color, whereas in my dumb way of encoding I was using 2 bits per color. So clearly I am doing better. Okay. Now let us take an example. I will give you some string of code words and you will have to guess what color of ball is this. Okay. So let us look at this sequence of number 0 1 1 0 1 0 0 1 1 1. Now note that for black I am using code 0, for red I am using 1 0, for blue I am using 1 1 0, and for green I am using 1 1 1. So let us look at this. The first bit is 0. So what color is this? This is black, because black I am representing by 0. So this is black. Next I have 1. Am I using any 1 to represent any code? So 1 could be red, could be blue, could be green. Let us look at next bit. So next bit is 1 1. Now which code word, which color has code word starting with 1 1? Blue has 1 1 0 and green has 1 1 1. So let us look at another bit. So this is 110. So what is 110? That's blue. Okay. Now let's look at next bit, that's 1. So now again this could be red, this could be blue, or this could be green. So let's look at other bit, 10. What is 10? 10 is red. So next ball is red. Next we have 0 here. So what is 0? 0 is black color ball. And next we have 1. So 1 could be red, could be blue, could be green. Let's look at next 2 bits. 1 1. Now 1 1 could be blue or could be green. Let's look at next bit, which is 1 1 1. And what is 1 1 1? That is green. So this is the, you can see this is the sequence of colors which have been encoded using bit this frequency. Another interesting thing you note here is I am using a variable length code. For black I am using 1 bit, for red I am using 2 bits, for blue I am using 3 bits, for green I am using 3 bits. So I am using a variable length code to describe the color of the ball. But because none of these code words are prefix of another code word, I am able to make out the boundaries, or I am able to make out when is a particular code word ending. So you can see using, this is an example of a variable length coding where we use variable length code to describe the color of the ball, and you can see that we are getting advantage in terms of number of bits we are using to describe the color compared to this dumb way of describing where we are not taking into account the fact that black balls are more likely to happen than, let's say, blue balls, green balls or red balls. Okay. So the message is like this. So the main principle of data compression is, can you read this out? Only information essential to understand must be transmitted. Note that I have deleted some letters, but still you are able to understand what is written. So that's the basic idea behind compression, that we would like to represent our source with minimum number of bits. So this was an example to illustrate how source compression is done. Now let's move into the next part of information theory, which will deal with describing or calculating the channel capacity. So let us explain what is a channel and what is a channel capacity. So the transmission medium over which we are communicating is known as channel. So channel is the medium over which we are communicating. Now Shannon in his landmark paper in 1948 described this concept of channel capacity, and he showed that if you try to transmit at a rate below channel capacity, then you can get arbitrarily low bit error performance as long as you consider very large block sizes. So channel capacity is a measure of how much information that we can transfer from the input of the channel to the output of the channel. So this is a measure of amount of information that can be conveyed between the input of the channel and the output of the channel. And Shannon in his landmark paper has mentioned that there exist channel coding schemes which can achieve arbitrarily low error probability provided the transmission rate is less than channel capacity. So channel capacity is the fundamental limit of data transmission. We cannot communicate reliably over a communication channel if the transmission rate is above channel capacity. So for example, if we say a channel capacity of particular communication link is 2 gigabits per second, then we should be able to send at any rate less than 2 gigabits per second, and it should be able to reliably communicate. So let us look at the block diagram of a communication system. So this is an information source that we want to transmit to a receiver here. So what is the first step involved? So this source encoder, what it does is it tries to represent the information source in a compact fashion. For example, in an English language, the letter Q is always followed by U. There is no word starting with Q which does not have U as second letter. So if you want to transmit, let us say a word starting with Q, it is redundant to send U, because Q will be always followed by U, right. So the whole idea of source encoder is to basically represent your source efficiently in minimum number of possible bits. And in this course we are going to spend quite a bit of time in talking about these source encoders. We will talk about practical source encoding algorithms, we will talk about what is the fundamental limit. If you try to compress beyond that, you cannot get a lossless compression. Once you have the compressed bit, the idea of this encryption is to secure basically. So you do not want those bits to be deciphered by unwanted users. So this is for security, you do some encryption. The idea of channel encoder is to introduce some redundancy in the source in a controlled fashion, so that with the help of those controlled redundant bits you should be able to detect or correct errors. So after this channel encoder you have what is your modulation. So you want to transmit those bits over a communication channel, you do modulation. Now once you modulate this signal, the signal passes through your transmission medium, which is channel. Again we will spend some time in characterizing what is the capacity of this transmission medium in this particular course. And once, so the output of this channel will be a noisy version of the transmitted waveform. So after demodulation you would try to correct and detect errors in your message source. So once you do that, you give an estimate of your information bits. Now de-encryption is opposite action of this encryption, and so this de-encrypted bits comes to the source decoder, which will then try to recover back your original sequence from the compressed bits, and that is basically delivered to your receiver. So this is broadly the block diagram of your communication system. In this particular course we are going to spend good amount of time in this source encoder and decoder, and as I said we are going to spend some time in characterizing the capacity of your communication transmission medium, which is basically channel. So let us quickly run through the various functionality of these blocks of digital communication. So as I said, the idea of source compression is to minimize the number of bits required to represent a source, and this process is known as data compression or source coding. And we are going to talk about various examples of source coding in this particular course. For example, Huffman code, impulsive algorithm. Now the output of source encoder, we normally refer them as information sequence. Encryption, as I said, the idea of encryption is to make the source bits secure, okay, and that's the idea of this encryption. So we convert these source bits into what looks like a meaningless data, which we call as ciphertext. So this process of converting your message text into some random looking text, which we call as ciphertext, is known as encryption. We would not talk about encryption in this particular course. Some examples of encryption is this data encryption standard and RSA system. Channel coding, as we said, its idea is to introduce redundancy in the message bits and use those redundancy to correct errors. So whatever transmission errors happened, the idea of this channel encoding is to introduce some additional bits into your message bits and use those redundant bits to correct or detect error. This is also known as channel coding or error control coding. So as I said, we introduce some redundant bits to a sequence of information bits in a controlled manner. This is important because we will have to use those redundant bits to actually detect and correct error. So when we add these redundant bits, we have control over what redundant bits we are adding. Some examples of channel coding schemes are, for example, repetition codes, where in repetition code we repeat what we are sending. Reed-Solomon code and cyclic redundancy codes. The output of the channel encoder is referred to as code word. Modulation, as I said, we want to send these coded sequence over the channel, so we map these code words into waveforms. Some examples of digital modulation schemes are phase shift keying and quadrature amplitude modulation. This you must have studied in a digital communication course. Channel, as I said, is the medium over which we are sending our waveforms, and this medium could be wireless or it could be a wireline channel. Now what does channel does? Channel essentially corrupts the waveform that we are sending because it adds noise, there are effect of interference from other signals, there is effect of fading. So our transmitted waveform will be corrupted by the channel. Some very simple models of channels are these binary erasure channel, additive white Gaussian noise channel. We will talk about them more when we talk about channels and channel capacity, how to compute their channel capacity. Now demodulation is basically opposite action of modulation. So you get a noisy waveforms, you want to convert them back into sequence of bits, that's basically demodulation. Now if you convert those noisy bits directly into zeros and ones, that's known as hard demodulation, and instead if you quantize the demodulation output into multiple levels, that is basically known as soft demodulation. The objective of this channel decoding is to correct and detect errors which are introduced by the channel. So that is the objective. So when does error occur? If your estimated code sequence is not same as the transmitted code information sequence, then errors have occurred. And we can find out error using these two metrics, bit error rate or frame error rate. So bit error rate is essentially fraction of transmitted bits that are in error is known as, is basically, so number of errors divided by number of bits that we have transmitted is basically your bit error rate, and frame is a block of data. So if there is any error in a block of data, we say that the frame is in error. So number of frames or number of blocks which are in error divided by number of blocks that you are transmitting, that's basically will give you frame error rate. So as I have already defined, the bit error rate is the expected number of information bits decoding error per decoded information bit, and frame error is basically if it's the percentage of frames which are in error, and frame is a block of data. So de-encryption is the opposite action of encryption. So once you get this cipher text, you want to get back your original text. That is the objective of this de-encryption. So you want to recover the plain text from the ciphertext with help of some key. That's basically your de-encryption. And finally, source decoding. So what you get at the input of the source decoder is compressed bits. Now you want to recover back your original sequence. That is done by source decoder. So you want to reconstruct the original source bits from the decoded information sequence. That is done by source decoder. Now due to errors introduced by the channel, there might be some errors introduced in the final reconstructed signal. So it's possible that your signal may get distorted as a result of that. Okay. So to conclude, basically in this course we are going to concentrate on the source encoder decoder part of a digital communication system, and in the transmission medium to characterize what sort of rates, what sort of data rates we can achieve over a communication link. Thank you.